Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video introduces the concept of variance and demonstrates how to use and interpret it. Let's get started. We already know standard deviation. Now let's meet the cousin called variance. The variance of a data set is simply the square of the standard deviation. Now, this is a very useful relationship. If we have only one of these values, we can easily get the other. If we need the standard deviation but have only the variance, we just take the square root of the variance and there's our standard deviation. Conversely, if we need the variance but have only the standard deviation, we just square the standard deviation and there's our variance. Now, this very useful relationship is reflected in the symbols we use to represent variance. Sample variance is going to be denoted with little s squared. Sample standard deviation is little s, and so sample variance is little s squared. Likewise, population variance is going to be denoted with sigma squared. The population standard deviation is a lowercase Greek letter sigma. Population variance is therefore a lowercase Greek letter sigma squared. Now you may be wondering, what's wrong with using just the standard deviation? Why would you make a new measure of variation by squaring a perfectly good measure of variation you already have? Why not just stick with standard deviation and call it good? Well, as we'll learn in a future mini lecture, the sample variance is an unbiased estimator of the population variance. But the sample standard deviation is a biased estimator of the population standard deviation. We'll talk in more detail later in this course about what this means. For right now, just know that the value of the sample variance will tend to approach the value of the population variance as you take samples of larger and larger size. You don't get that effect with standard deviation. Remember that a main reason why we take samples is so we don't have to collect data from the whole population. We want to make conclusions about the population without taking data from every member of the population. Variance allows us to glimpse the standard deviation of the population from a sample because the variance is an unbiased estimator, so it will tend to approximate the true population value. We then take the square root of the population standard deviation to get the population variance to get the population standard deviation. And we can't do that just using the sample standard deviation, because that standard deviation is a biased estimator. Now, what is it that creates this unbiased effect in the variance? Well, it's because when we're calculating the sample variance, we're using n minus 1 on the bottom of our fraction instead of just n. If we use the full sample size instead of one less than the sample size, we end up underestimating our population variance. Again, we'll get into all this later in the course. For right now, I just want you to focus on the relationship between the variance and the standard deviation. And to help with that, we're going to go back to our earlier chocolate chip cookie example because, hey, chocolate helps with just about anything, right? I mean, you feeling me here? Oh, yeah. Okay, standard deviation we saw for our chocolate chip count from 5 cookies is 1.7. To get the variance, we could go back to the data and either use some equation requiring tedious calculations or technology like StatCrunch, or we could just skip all that, square the value, since the variance is standard deviation squared. Well, 1.7 squared is 2.9, so the variance is 2.9. It is seriously that easy, and that's what I want you to focus on with variance for right now. Let's apply what we've learned about variation to an example problem. So here we're asked to find the range, variance, and standard deviation for the number of years elected U.S. presidents live after the election. Pause the video here, go open the POTUS file in StatCrunch and see what you can do about solving this problem. Then come back here and we'll retrace the steps that lead to the right answer to see how you did. Okay, how did you do? Well, once the data is in StatCrunch, you should click on Stat, Summary Stats, Columns. Then in the Options window, select the column with your data, pick your statistics, and then press Compute. Then you get your results, which should look something like this. If you're out in left field here, pause the video, go back to StatCrunch, and try this again until you get this down. Now, notice the order in which the statistics were selected matches the order in which those same statistics appear in the problem statement. That's a trick that makes it a little easier to put your answers in the answers fields in your My Math Lab assignment. So this way you don't confuse values with each other when you're entering them in. Okay. Now, is the standard deviation a good estimate of the variation of retirement years in the general public? In other words, is the standard deviation that we've calculated here a good estimate of the variation of retirement years in the general public? I'll give you a moment to respond. Well, I hope you said no, because that's exactly what we need to hear. Your sample here is from presidents of the United States. That's not characteristic of the general population. That's a very specific subset of the population. So the sample is not representative of the entire population. Whatever conclusions we make from this sample should not then be applied to the larger population, because our sample is not characteristic of the larger population. Now, what would the standard deviation be if every U.S. president lived the same number of years after leaving office? I'll give you a moment to think about that one. Well, I hope you said 0, because that's what the answer is. This should make sense if you think about what the standard deviation is measuring. It's variation in the data, or how spread out the data is. Well, how spread out your data is, how spread out is that when every value is the same? It's not spread out at all. There is no variation if everything is the same. And so the standard deviation, along with every other measure of variation, would be 0. Let's look at one more example. This one involves a speed dating study conducted by Columbia University, in which female participants rate the attractiveness of their male dates on a scale of 1 to 10. We're asked to find the mean, median, mode, and mid-range for a sample of those data. You could find that sample in the speed dating file in our StatCrunch group. So pause the video, go open that file, calculate the statistics asked for here. I'll wait here until you get back. Okay, how did you do? Well, I hope you got something that looks like this. If not, go back to StatCrunch and try again until you do. The mid-range, of course, you must calculate yourself, but that's easy enough to do once you know how. Now, pause the video, go back to StatCrunch, and answer this question. Calculate the range, standard deviation, and variance for the same sample data. Okay, I'll be here when you get back. Okay, I hope you got something that looks like this. If not, go back and try again until you get it. Now, can these results be used to describe the attractiveness ratings for the population of male adults? I'll give you a moment to respond. Well, they can't. What sampling method was used to get your sample? Speed daters are all volunteers, so this sample is an example of voluntary response. And as we discussed before, voluntary response produces samples that aren't very characteristic of the larger population. That brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.